Hi, welcome back to Moose and Chemistry. This is Nuclear Chemistry Isotope Stability Lesson 1. Alright, what is nuclear stability? Well, nuclear stability is the stability of the nucleus determined by the ratio of the neutrons to the protons. Factors that affect nuclear stability? Well, strong nuclear force. Strong nuclear force is a force that is fundamental in nature between protons and neutrons and their quarks. This force is not clearly understood and still being explored, or I would try to explain it to you. Electrostatic force, that's the force that is between protons trying to push the positive light charges apart, which we call repulsion, in the nucleus. And the strong nuclear force keeps the repulsion in check/balance so the nucleus does not fall apart. Well, if the ratio is 1:1 neutrons to what we call the Z number, the atomic number, it's the number of protons, then it's stable, or up to 1.5:1 neutrons to the atomic number Z. When the nucleus is stable, that's what you have to have, this ratio between those two areas. If the ratio of the N to the Z is outside this narrow band, then the atom's nucleus is unstable and will fall apart or split. These elements are considered radioactive unstable. Quick checklist: if Z is equal to N, then it's very stable. If N is greater than Z, then it's going to be stable, more or less. But if Z is above element number 83, then it cannot be stable. Okay? And on this chart right here, in the gold area, this is the area of stability. Any atoms above this line of 1 to 1.5 or below the line of 1 to 1 are considered unstable. All right, so let's look at three problems here. We have iron 56, californium 252, and lead 207. So we took these three elements. So let's go ahead and do iron 56 first. So we got Fe. 56 is our atomic mass unit, number of protons and neutrons. Our atomic number of iron is 26. So if we want to know the number of neutrons, we have to go 56 minus 26, which will give me 30 neutrons. Then we do the N over Z to see our ratio. So we take our number of neutrons, which is 30, divided by our atomic number, which is Z, which is 26. We're going to get a 1.15 ratio there. So this is considered stable. All right. Let's look at californium 251. Okay, californium 251 is element number 98, of course. So we take 251 and we put this over 98. All right, well, hey, guess what? You know, since the Z number is above 83, which is this case is 98, you know this is unstable, but let's go ahead and prove it. So you go 251 minus 98, we're going to get our neutrons here, and that's going to give me a total of 153 neutrons. Okay, so far so good. So we go N over Z. So we get 153 divided by our atomic number, Z number, which is 98, and this is going to give me a 1.56 ratio, and that's considered unstable. Okay, our last element we're going to look at is lead 207. Now, everybody thinks that lead is stable, but let's see what happens if we have lead 207. All right, so let's go ahead and do this. So we have lead 207, so we're going to call this, of course, Pb. We're going to put 207 on top and 82. Now, you know what? That 82 is pretty close to that 83, but it's not at 83 or 84. So let's go ahead and see if this is going to be unstable. All right, so let's go ahead. Let's figure out a number of neutrons. So we take 207 minus 82, and that is going to give us 125. 125 neutrons. So remember, it's N over Z, so we're going to take 125 divided by 82, and this is going to give me 1.5 1.2. It's outside that range of 1.5. So this is unstable. Well, that's it for this lesson. You guys be snarly, and we'll see you back here at Musin Chemistry.